Can you see my screen?
Yes, sir.
Okay, so today we'll be starting with a new topic related in hydrogeology that is known as geomorphological principles, where we'll be performing the different kinds of drainage using morphometric analysis. Like in the earlier classes, you have already studied that in the earth surface you have got various kinds of drainage patterns are available on different kinds of landforms, different kinds of geological types. So whenever you are going for such kind of analysis related to different terrain, like if you go in Himachal, you compare that with the desert in Rajasthan, and then in the Western Ghats, you'll find there is a difference in lithology, there is difference in landforms, there is difference in rock type. So in order to have a basic understanding about the mechanism of what is the amount of runoff that is generated from any watershed, you have to primarily perform drainage basin morphometric analysis. So we will be studying much into the detail about what are the different topics. So we'll start with the basic definition. What is a drainage basin? So a drainage basin is the area of land that gathers the water from precipitation and deliver it into a larger streams or lakes. Generally, it happens for each and every river system. So whenever you are going for drainage basing or watershed analysis, the remote sensing and GIS techniques is the best technique to map and differentiate the different kinds of basins, catchment, subcatchment, watershed, sub-watershed. So because that is a regional in nature, so if you go into the field you cannot have the exact aerial extension, because maybe if you go for the river systems, for example, if you talk about Ganges, you talk about the various river systems that Satluj, Kosi, that originates from the mountainous terrain, even if from Tibetan plateau and merge into Bay of Bengal. So that is a large area that cannot be viewed personally, or you cannot map it, you cannot see it in the field. So the best technology to be used for mapping such kinds of drainage analysis or basing analysis, where you will be demarcating the different kinds of drainage, the drainage type, the different kinds of orders, the different kinds of measurement. If I say that you have to measure the length of a river, if I say into the field, you cannot physically do it. So the only technique that is left is a satellite images. So we'll be using the satellite images to perform this drainage basing morphometric analysis. So when you talk about, now we know what is a drainage basin. Now you have to know about what do you mean by morphometry. So morphometry means measurement and mathematical analysis of the configuration of the earth surfaces, shape, dimension of its landform. That is the definition given by Clark in 1966, where in drainage morphometric analysis, we are going to measure each and every component of the earth surface, whether that is the length of the river, that is the area of the surface, what are the different kinds of shape, what is the different kinds of dimension. So all such kinds of morphometric analysis will be performed, and finally we'll be performing the basic morphometry, where measurement of three-dimensional property of the land of a fluvial erosion systems will be evaluated. So whenever you are going for any kind of measurements, our land surface, whenever you are going, is a 3D representation. That 3D means that for each and every land, the height is different. So in order to measure that height, you need a three-dimensional property, because the earth is having a 3D. So we'll be measuring this 3D measurements of the fluvial erosion ecosystems. So what are the variables that are very important to be studied whenever you are talking about drainage morphometric analysis is the stream order. Stream order is the number of streams, smaller streams which are connected to the major stream or the main stream. So that is denoted by stream order. Then the next variable that is associated with it is a stream length. Stream length is the total amount of streams, whether they are minor streams, whether they are tributaries, whether that is mainstream. We'll be calculating the entire length of each and every object, each and every feature. Then comes bifurcation ratio, where we'll be dealing with the number of orders of streams that are available into a particular river system. What are the number of streams that are having a stream order 1, what is 2, what is 3, we'll be doing that. Then we'll be calculating the stream length ratio, then basin length of the area, valley side slopes, basin area, stream frequency, drainage density, elongation ratio, circulatory ratio, form factor, and relief ratio. These are the different variables that has to be analyzed in order to understand the drainage morphometry of a river basin. So we'll be doing much into the detail what is about the different kinds of variables. We'll be reading that into detail in the coming slides. Now the next is the morphometric features can be divided into three types. You will have all these variables what we have stated earlier in the previous slide can be divided into three categories. The first categories is linear properties, means which are in line, and those features are one dimensional. Then you have got aerial properties, they are two dimensional. And finally, the relief property, whenever we are talking about relief, relief means topography, means height. Whenever there is a height, means apart from x and y, you need a z. That's why that is represented as a 3D or a three dimensional. So you can see that this is a watershed differentiated and delineated using the satellite remote sensing, or you can use topographical sheets to demarcate the different kinds of streams, the watershed boundary, the rivershed area, and the different kinds of order. So you can see that these are in between, these are the streams, and this the outer boundary is denoted as a watershed area. So you can see that when you will be using the satellite images, it will provide the real representation of the terrain, and you can easily demarcate the different objects and different earth units. So you can see that all these river systems, the tributaries are connected to each other, and finally they drain, and finally they meet at this point, and this is the total area of this watershed. So this is denoted as a watershed. If you want to go into the much smaller unit, then you will be saying as sub watershed, micro watershed, mini watershed. So that depends on the area. We'll be doing those classification, the category classification will be doing in coming lectures. So now we know that we have got three kinds of property. One is linear, other one is aerial, and third one is three-dimensional or relief property. Now, when it comes to linear properties, what we are talking about, that includes stream order, stream number, stream length, length ratio, bifurcation ratio. So whenever you are going for the measurement in terms of linear property, you have to measure, you have to calculate the stream order, you have to calculate the stream number, you have to calculate the stream length, length ratio, and bifurcation ratio. So what do you mean by stream order? So stream order means hierarchy ranking of the streams. That was given by Staller in 1964, where the order changes at the confluence of a stream. So whenever you will be seeing in the coming slides, I will show you how the stream order is provided. The first order streams are ones that do not possess a tributary. So the first order, whenever you're seeing the main river, that main river gets the water from the first order and second order, or you can also say as from the tributaries. Now we are going to map and identify each and every tributary that is connected to the main river. Now that is denoted as a stream. So the first order stream is the origin of a river, you can say. And when two first order stream meets, a second order begins. Now we'll be reading much into the detail. Now you just visualize how this ordering is performed, or what is the logic of giving these numbers. So if you go for the Staller order method of 1957, this is designated first order stream as those lacking a tributary. So whenever you want to give, means we want to identify each and every stream that is connected to a river. Generally, this first order streams, right now what you are seeing on your screens, are those rivers or those streams that gets water only during precipitation, or only during the monsoon period, or only during the precipitation period. The higher order streams like 7 or 3, what you're seeing, are the main rivers that has the water throughout the year. So that is known as, you have got two kinds of rivers, you can say. One is perennial and one is seasonal. Seasonal are the first order streams, or the first order, you can say, the river types more precisely, you can say, that are those rivers that gets water only during the rainfall seasons, and that gets dry up over the coming months. So whenever you will start up giving a number to the different kinds of streams that you see on the earth surface, you have to start from the outer boundary. The outer boundary, you can see we have given 1, 1, 1. These are the outer boundary that will start from outer boundary and will go towards the inner boundary. So whenever, when you see this, we have given 1, this is we have given 1. So whenever 1 and 1 meets, it gets converted into the next higher order. Thereafter it becomes 2. So when there is a 2 and there is a 1, always the higher order will be continuing. So that's why you will be seeing that as a 2. Now again come to this side, this is a 1 and 1, it makes 2, 2 and 1, again it will be continuing as a 2. Again you have got 1 and 2, again it will be continuing as 2, and whenever it will be 2 and 2, wherever it meets, it will be continued as 3. So you have to rank each and every portion of the streams, you have to identify, you have to give a name. This is, you can say that it's just like giving a name to each and every stream with the scientific logic. So second order at the confluence of first order, and so on, you can see. And in the same way, you have to go on and on and on. You will be going up, and you have to classify. Means if you have got the higher order coming up in the main river, like if it comes to 9 or 8, means that is a very old river. Okay, and that has got a lot of streams and tributaries connected to it, and that is a very large river. Getting it? Got it?
Yes,
Yes.
yes.
Okay. Now it comes to stream number. Now we have provided now order. Order is providing the name to each and every stream. How the ordering is done. Now we know that whenever there will be a meeting of two same order, it gets converted into the next order. It will be going on with the same order. If there is a lower order, you will be continuing with the higher order. And whenever we have got the same orders meets at a place, you will be converting that into a next order. So that is the way you are providing the names to those stream orders. Now stream numbers, what do you mean by stream number? Stream number means the total number of stream segments present in each order. What are the total number of stream present in each order, that is denoted by stream number. Now for example, using the Trellis system, we can see that order 1. Now you calculate what is the total number of order 1. So we'll be calculating it: 1, 2, 3, 4, 5, 6 and 7. So we have 7. Order number 1, total streams are 7 in number. Now we'll go for order 2. Order 2, now we'll calculate 1, 2, 3, 4 and 5. So you have got order 2 as 5 stream. Now order 3. Now order 3 is 1 stream. So what it says, whenever I will be checking anybody, I can evaluate that whether he has perfectly calculated or there is some misclassification. How will be judging it? Means the lower number of orders will have the highest number of streams, and as the order increases, the number of stream reduces. So in case you have calculated any stream number, and after calculation, if I found that your higher order is just vice versa of what it has been represented in the current diagram, I can clearly say that you have falsely or you have misinterpreted the entire codings. So what you have to do, you have to recode again. So by seeing that, I can say, so whenever you have to check the accuracy, the lower streams will have the higher number of streams and the higher orders will have lower number of streams. If the result is not coming with what it has been stated, means you have done something wrong while you were classification. You have to recheck it again. Got it? Yeah.
Yes, sir.
Understood? Now comes stream length. So stream length is nothing else. Now using remote sensing and GIS, we can calculate this length. So whenever you are tracing it, whenever you are mapping it, whenever you are digitizing it, as you have provided the projection system, as you have provided the measuring unit, whether you want in meters, whether you want in kilometers, each and every length of each and every order is directly calculated using GIS software. So using the GIS software, you can easily calculate the total length of stream in a particular order. Now, as we have calculated it, I know now what is the total length of stream for one, what is the total length of stream for order 2, what is the total length of stream for order 3, so on, until unless each and every stream is classified. And what does it suggest? It reveals the surface runoff characteristics. So what the prime focus for doing such kind of analysis is during the rainfall, you can see that those near to your houses, you will see like river like flowing up. There are a lot of water that is coming up, and post monsoon there is no water. So what is that? That is excessive water that is beyond the carrying capacity of a land, and that is denoted as runoff. Now because our population is increasing, because our we are creating more of cementing surface, this runoff has to be preserved. Otherwise you will not preserve this runoff, it will go and meet into the oceans and your water table will not get recharged. So in order to get a recharge, you have to have a runoff characteristics. Now the total length of a stream segment is maximum in first order stream and decreases as the stream order increases. Yes, obviously, as you have seen that in the current figure, the number of streams are high for the lower orders, that is the first order. That's why obviously the number for the class which has got the maximum number will have the maximum length, and the class which have got the minimum number will have a minimum length. Now next is mean stream length. So how it is calculated? It's very easy. By dividing, it is calculated by dividing the total stream length of an order by a total number of stream of an order. Means total length by total number. So how you will be calculating the mean stream length? This is the formula that has to be applied. So here the mean stream length is the formula is total stream length of an order divided by total number of stream length of an order. Means right now if you have got for example, what is the total number of order? That is 7. And for example, if it has gone as 11 kilometers, so now we'll be dividing that with that unit. So you will be getting the mean stream length of each and every order. Now the next calculation that we have to do is length ratio. So how you will be calculating this length ratio? The length ratio means ratio of mean length that we have calculated already for one order to the next lower order of a stream segment. Means what we will be doing, what the formula here we are trying to calculate, that is the ratio of mean stream length of one order to the next lower order of the stream length. Means the stream length of 2 will be divided by the stream length of 1. So this variation in some basin may result from the change of slope and topography. So here RL denotes stream length ratio. The formula is total stream length of an order U by total stream length of next lower order. So what you will do, you will take a stream length of order number 2 divided by stream length of order number 1. Then stream length of order number 3 divided by stream length of order number 2. Getting it? Yes?
Yes, sir.
Anybody? Understood?
Yes, sir.
Okay. Now next is bifurcation ratio. So it will be more clearer in concept when we'll be doing some exercises related to drainage morphometric analysis. Now next is bifurcation ratio. So how this bifurcation ratio is calculated? This is a ratio between the number of streams in one order to the next higher order. So what we have done, like already we have done, like we'll be dividing this 7 by 5, 5 by 1. This is what is the meaning of bifurcation ratio. Means the ratio between the number of streams in one order to the next higher order. So not same for one order to the next order, and it depends on the geological features of the drainage basin. So what is the formula that is adopted for bifurcation ratio? That is the total number of stream segments of an order X by the number of segments of the next higher order. Like total number of streams of what we'll do, 1, like this will go again to back 7 by 5, 5 by 1. Getting it? Now this is how we'll be calculating the different kinds of stream order. So for calculating the bifurcation ratio, it says the number of stream of one order by divided by number of stream of second order. So what was the number of stream of first order? That was 7. Now what is the number of stream in the second order? 5. So the answer is 1.4 for first order to second order. Now from second order to third order, what is the bifurcation ratio? That is 5 divided by 1, that is 5. Now when it comes to mean bifurcation ratio, what you have to do? You have to divide this, like 5 plus 1.4 divided by 2. Mean means average. So in order to get an average, that is average 6.4, the average will be 3.2. Now the mean bifurcation ratio for the current tributary, for the current example, will be 3.2. Getting it? Understood?
Yes, sir.
Yes, sir.
Now this were the properties that were made for linear properties. Now we'll be studying the aerial properties of the different drainage basins. So what is the aerial property? Aerial property is related to the area. It's related to the area. So what you have to do whenever you are going for aerial property, first you have to delineate the drainage area, that is AU. So what is the drainage area? That is the entire area drained by a stream or system of stream such that all stream flow originating in an area is discharged through a single outlet. Now what is this? This is, I'll go again to this figure. This is the outer boundary that we have created. So this is what we are trying to calculate in aerial. This is the area that has to be delineated, and this is known as drainage area. Okay, got it? So we'll be calculating the drainage area first, then we'll be calculating the drainage density. So drainage density is the expressions of closeness of spacing of channels. So you will be seeing that whenever there is a flood pictures coming or videos coming up from Himachal or Uttarakhand or Jammu Kashmir, and then you see a flood of UP, Bihar, you'll see the intensity of the rivers are quite less in the plain areas when compared to the hilly terrains. That is because the drainage density is very high in Himalayan terrain when you compare that with the plain terrain. So drainage density is the number of stream. The more the number of stream, the more the dense the streams are, it will be creating more runoff. The lesser the number of streams are, means there is more spacing, and that's why the intensity will be less. Now, what does this drainage density provides? It provides a quantitative measure of the average length of a stream challenge of the whole basin. So, drainage density means the formula that will be deriving or will be using it to calculate the entire drainage density is the total length of a stream by drainage basin area. So if we calculate that, we can calculate the drainage density. Now second or the third one is stream frequency or drainage frequency. It will be more easier to understand the drainage frequency. Drainage frequency is the number of stream segments per unit area. Just like you can say population density. So if you say 980 persons per square kilometer and you say 500 persons per square kilometer, means in that given area of place, what are the total number of people residing in that area? So in case the population density is high in any area, if there is a disaster, the damage will be very high in the portions where the number of persons is high, means where the population density is high, because the number of persons living in that area is high. In the same way, for the drainage frequency also, if the drainage frequency is high, means it suggests that the number of streams or the number of river that is generating water is of intense quantity and quality. So the stream frequency, the formula will be the total number of streams of all orders, means the total order of streams that are available in particular area in square kilometer. Means a higher drainage density may imply an increased stream frequency. Now next is drainage texture. So what do you mean by drainage texture? Now the drainage texture means the total number of stream segments of all orders per parameter of that area. So here what we are saying for the texture, we are not using the area, we are using parameter, and that are influenced primarily by infiltration capacity and soil type. So the formula that will be used to calculate the drainage texture is the total number of stream of all order, means 1, 2 and 3 for the current example, divided by the not the area. For drainage frequency we were dividing the area, for drainage texture we are dividing the parameter. Getting it? That is in kilometers, and the previous one was in square kilometers. Now the next important variables that has to be calculated is circulatory ratio and elongation ratio. So what is the difference between the circulatory ratio and elongation ratio? So our circulatory ratio is a quantitative measure for visualizing the shape of a basin. So by seeing the shape, you can see and you can visualize the shape of the basin, whether that is a round shape, whether that is a triangle shape, whether that is a rectangular shape, and it is expressed as the ratio of basin area to the area for circle having the same parameter as the basin, and this is influenced by length, frequency and gradient of the streams. Now it comes to elongation ratio. Elongation ratio denotes a ratio of the diameter of a circle of the same area as the basin to the maximum basin length. A circular basin displays better efficiency in discharge of runoff than an elongated basin. Now comes basin shape, how the basin shapes look like. So the basin shapes is a measure of elongation of a basin. As the elongation increases, the basin shape decreases. Means if it is more inclined or near about elongated, more circular, the density will be less, and if it is small, the density will be high. Now, the length of a basin is a measure of linear distance between the mouth of the basin and the most distant part from the mouth. Now, length of overland flow. So, what do you mean by length of overland flow? It is the distance from the cross line at which the concentration of flow occurs. Now, downslope, the run of concentrates to form reels and gullies after precipitation, and the length of overland flow that you see during the monsoon period is approximately equals to the half of the reciprocal of the drainage density. So these are the all parameters that were related to the shape of the basin. So whenever you are creating, so you have to calculate the drainage area, then you have to calculate the circulatory ratio, then you have to calculate the elongation ratio, you have to calculate drainage density, you have to calculate drainage texture, you have to calculate stream frequency in terms of aerial aspect. Now, the third aspect on the basis of which we'll be performing the drainage morphometric analysis is basing relief. So, what does basing relief suggest? It is the elevation difference of the highest and the lowest point of the valley. So generally for this also we have got various kinds of digital elevation models that are available in remote sensing and GIS, that is known as digital elevation models, where the information about the terrain, about the topography, about the relief is available at different resolutions free of cost for the entire globe. Now, the minimum resolution that is available is 1 meter from cartosat to 30 to 90 meters for SRTM, DM or Aster GDM, that is Global Digital Elevation Model with a special resolution of 30 meters. So, using those digital elevation model, you can easily calculate the difference in the elevation of height from the highest point to the lowest point in the valley. Now what you have to do, you have to subtract the elevation of the mouth of a basin from the highest point within the basin. Now the second important parameter that has to be calculated is relief ratio. So what do you mean by relief ratio? That is the ratio between the total relief of the basin. Okay, what is the topography of the basin? And it is calculated as the elevation difference of the lowest and the highest point of a basin and the longest dimension of the basin principal to the drainage length. So the formula that will be used for calculating the relative relief is the maximum basin relief divided by maximum basin length. And at last, we can conclude on the basis of all these linear, aerial, and relief parameters that morphometry is essentially a quantitative involving numerical variables whose values may be recovered from topographical maps. That's why whenever you are going for drainage morphometric analysis, you have to take a satellite image, you have to take a topographical sheets, you have to take the various digital elevation models, you have to take the various survey of India maps of different scales for calculating the entire mathematical calculation, because whenever it comes to runoff, whenever it comes to water, that is a unit that comprises area, that comprises volume, and the relevance of morphometric variables is therefore uselessness for comparison and statistical analysis. So whenever you are doing such kind of analysis, you have to perform, you have to use the different data sets, whether that is from the satellite images or whether that is from the topographical sheets. You have to use all these data sets, you have to use all these data images for calculating this uh, drainage morphometric analysis. And with this, I'll end my today's presentation. I'll be stop recording it.